Okay, today we're going to talk about differentials. So, whoop, we already did that. Okay, today we're going to talk about differentials. So we talked about linearization and linear approximations yesterday. Today we're going to talk about differentials. So, we're currently taking a course called Differential Calculus. We'll be taking Integral Calculus second semester. It's wrapped up into what they call Calculus 1. If you were to be an engineer, any engineers here? Okay, so you guys will be taking a course called Differential Equations. This is like a one-day small introduction into differential equations. Okay, and like I said, you guys get to use your notes on the test. Between related rates and this stuff, it's just a very small segment of something we need to cover in calculus. We'll move on to more kind of the meat and potatoes calculus after that. So if I pick a value, say x, and I draw the tangent line, a function has a certain change ascribed to it. And we call that change delta x. For those of you in physics, you may be familiar with this. It's the triangle is a capital D or capital delta in Greek, which is interesting because the Greek alphabet didn't really come up with capital letters till much later in its kind of existence. We say that that's the same thing as dx, and I'll show you why. Delta x and delta y, they refer to the change in the function. Delta x and delta y refer to the change in the function. I'll say it one more time. Delta x and delta y refer to the change in the function. Dx and dy refer to the change in the derivative value. So you can see if the line, the linearization, the slope of that line represents the instantaneous rate of change of the derivative at the value of x. And as we move along or extrapolate a certain distance dx, you can see that those, as we move along, those become further apart. So why do we do this? Why would a differential for a function be useful? Dy helps us approximate delta y values in small intervals. So obviously, the larger we make dx and delta x, the further apart dy and delta y are probably going to be. Okay? So the question is, how do we come up with delta y? Well, it's very simple. We've used dy over dx to refer to a derivative, correct? So if we just simply multiply both sides, we get dy is equal to f prime of x dx. And that is how we find delta y. Dx referring to our change. So let's look at some basic examples, and we'll get more graphical on application. Okay. So it says A, find the differential dy and evaluate dy for the given values. So if we want to find the differential, we say first let's find the derivative. Dy over dx is, what's the derivative of 3x? What's the derivative of negative 1 over x? Good, 1 over x squared. So that means that the differential, or question A, dy is equal to 3 plus 1 over x squared dx. Question B says, evaluate dy for the given values of x and dx. So now to evaluate dy, where the change is going to be 3 plus, I plug in, what do I plug in for x? 2. So I get 1/4 times dx is 0.5, or 1/2. So 3 is like 12/4. 12/4 plus a fourth is 13/4 times a half is 13/8. You're going to try the next one on your own, but first, what rule would you use to find the derivative of 3 over x plus 1? You can use the quotient rule. I would encourage you to use raise 3u to the negative 1 and x plus 1. Let's try that. Let's move on to the negative 0.075 or negative 3 over 400. Let's try an example where we're actually looking at the graph. Yes. So what dy means is this, okay? I'll give you the example that we're going to do on the next page, okay? So let's say that x is 64, okay? Let's say the function f of x is the square root of x, okay? Then if you plug in 64, what's the output going to be? It's going to be 8, right? Well, suppose I don't want to know the square root of 64. Suppose I want to know the square root of 64.3. That'll be more difficult, wouldn't it? So the fact is I don't actually find the exact value of the square root of 64.3. What I do is I calculate dy, which is an approximation for how much I move up. So in this case, we're going to end up calculating how much we move up to find what that value is. So it's how much we move up from that output value. Yes. Yes, without a doubt. In this case, dy is an overestimation of delta y. And you may say, like, what's the application? Actually, I have a problem on here that involves measuring a circle. My, my cousin is a disk drive engineer. He engineers hard disk drives. So if you, like, say, you guys familiar with Seagate, it may have an external hard drive, like a 2 terabyte external hard drive. Okay, maybe made by, I don't know, Westinghouse or Seagate or, okay, it's Westinghouse. So, so anyway, so that's what my cousin does. He engineers these large hard drives that are either used by you guys or your servers, and they're constantly looking at kind of issues that come on up to refine them, and they're looking at these delta values all the time. Okay, their margin of error and what they're allowed to be, because we're never truly precise in all of our measurements, and so so we look at overestimation, underestimation, percent of error, all those pieces. So it's good stuff. So let's kind of get closer to where Clara's question is what does this dy represent? And we can see that in a graphical example, such as example 4. My cousin's an extraordinary guy. He's actually built 4 motorhomes from scratch. He likes to build things, and so he and I get along because I like to build things as well. We have fun together. We straighten cars. All right. So we have an x value of 1. We have a function of the x cubed plus 1. I'm going to use my delta x value. It says to compute delta y and dy for given values of x and delta x equals dx. Sketch a diagram showing the line segments and the lengths of dx, dx, dy, and delta y. So first of all, how far do I move over that way? I have an x value of 1, but how far am I moving that direction? 0.2. So from 1, I'm going to move over 0.2. So I'm not focused on 1 anymore. I want to focus on 1.2, okay? So this is delta x, which is the same as dx, which is 0.2. Sorry, my drawings get a little bit away from me. Now I'm going to draw a tangent line at that point, 1. And I come up with 2 segments. I come up with one segment that goes to my function, and I have another segment that goes to the tangent line. Do you remember which one is delta y? Is it the one that goes to the function or the one that goes to the derivative? It's the one that goes to the function. So this distance right there is dy. I'm sorry, delta y. We just said that. This is delta y. The one that marks the rate of change, which is modeled by my tangent line, is dy. So is dy an underestimation or an overestimation? Dy is an underestimation in this type of problem, okay? So we want to compute two things. We're going to start by computing delta y. Delta y is the change value in the function. The change value from up here to down here. Any idea how we would figure out how much that change is? Derivative is a good guess. We're going to do that for dy. But for delta y, we need to do something else. I need these two y values, correct? Do you know what the y value is here? 2. Why? You plugged in 1 and you got 2. So how would I figure out this y value? You'd plug it in. So you're going to do y of 1.2 minus y of 1. So I will plug in parentheses 1.2 to the third power minus or plus 1 minus 1 to the third power plus 1, which is 2. And I get 0.728. Now, you guys told me that delta y, which we just found, will be an overestimation. So we would expect dy to be smaller. Let's find dy. So Claire said in order to find dy over dx, I do take the derivative. What is the derivative of x to the third plus 1? 3x squared. Therefore, my differential is 3x squared dx. So dy is equal to, what do I plug in for x? So I get 3 times 1 times, what is dx? 0.2, or 3 times 0.2 is 0.6. Do those appear to be relatively close? Yeah, I guess, again, that's relative to what you're trying to measure. But it seems reasonable to us that with a very rough sketch, not a very accurate sketch, that this was an underestimation of that value. Okay? So we're looking at the raw algebra right now. We'll get to the application in the last 3 problems. Let's flip it over. Yes. 0.728 and 0.6. So 0.728 is represented by this red length. That's how much the y increase is if the x increase is 0.2. dy is the green segment. That's the estimation for the increase. Now, is 0.6 an accurate enough estimation? If it's not, then we would have to, close our interval a little bit more to try to get more accurate. Okay, let's try this one. What does the square root of x minus 2 look like? Yeah. Shift the 2 to the right. Draw a tangent line at 6. Now, what is my delta x value? What am I going to move over? 0.1. And for the sake of my drawing, you might hate that I'm going to do this, but we want to be able to see it well. if I move over 0.1, that's not going to leave us much space to really look, is it? So I'm going to make 6.1 right here because we can, right? That means delta x or dx is 0.1. So obviously our drawing is very skewed, but we're going to have a better chance of them viewing it. So this red segment, is that going to be delta y or dy? Did I draw to the function or to the derivative? I drew it to the function, so therefore it is delta y. As I draw to the derivative, then that is dy. Let's calculate delta y. Delta y would be the function evaluated at what? 6.1 minus the function evaluated at 6. Or in other words, the square root of 4.1 minus the square root of 4, which is obviously 2. So we get square root of 4.1 minus 2 will be 0.0248. So it looks like the increase is only 0.0248. I wonder what the estimated increase would be. In order to figure out the estimated increase, dy, we take the derivative. dy over dx is, what's the derivative of the square root of x minus 2? What rule do I have to use? Chain rule, I've got u to the 1/2, and I've got x minus 2. Derivative of x minus 2 is 1, and derivative of u to the 1/2. Good, 1 over 2 roots of u. So I end up with 1 over 2 roots of x minus 2 times, we have delta x, I'm sorry, dx. So now I'll plug in my values. So multiply the dx over, I get dy is equal to, what are we plugging in for x? 6. I get 6 minus 2 is 4, square root is 2, times 2 is 4. So 1 over 4 times, what is my dx value? 0.1 or 1 over 10. And I get 1 over 40, which is 0.025. So is 0.025 a good estimation? I think it is. I think it is. So let's get one application problem in before lunch. And it says use differentials to estimate the given number. So picture Isaac Newton, no calculator. He wants to come up with the square root of 64.3. Now we tried one way yesterday with linear approximations. Let's try it by using differentials today. First, I need to come up with a function. And I'm going to choose my function to be the square root of x. Then I got to come up with an x and a delta x, which is the same thing as dx. Now, I don't know the square root of 64.3, but I do know the square root of 64. How far will I move from 64? 0.3. And we'll pick it up there when you get back. Okay, so again, we're trying to estimate. Hope anybody have something exciting for lunch? What? Sweet potato fries and chicken wild rice soup. And you have lefse. I love lefse. We make lefse at home. All right. Square root of x, you know, square root of 64 is 8, but what we want to do is we want to move x 0.3, right? So the idea is that we know the square root of 64 is 8. So the square root of 64.3 will be 8 plus something. We moved 0.3 for x. We're going to move something for y. And we don't know that exact amount, but we're going to estimate it. So again, keep in mind that you are Isaac Newton and you don't know how to, you don't have a calculator. So, he says, well, I'm going to find a derivative. dy over dx is, what's the derivative of square root of x? 1 over 2 roots of x, right? So therefore, dy is 1 over 2 roots of x times dx. So the estimated change is, what do I plug in for x? 64. So I get square root of 64 is 8 times 2 is 16. So 1 over 16 times 3/10. And you get 3 over 160. So from 8, I move 3 over 160. So what we've said is that the square root of 64.3 is approximately 8 and 3/160ths. And now the most exciting part is that we check it on our calculator and take the square root of 64.3. We get that, and then you take 8 plus 3 divided by 160, and you get that. And that's pretty close, isn't it? And if you're somebody like Isaac Newton and you're like, well, how close am I? You could take your estimated value and simply square it and say I wanted to come up with 64.3. Feel like I'm there. Yo. Well, I mean, 8 plus 3, 1 over 1, or 3 over 160 is the same as 8 and 3/160ths, right? So, okay. All right, another example. Say we want to estimate 3.01 to the fourth. Obviously, you could take 3.01 and multiply it out 4 times, but here's another way to do it as well. We need a function. Anybody know what f of x is? X to the fourth, and the x value where we're evaluating this is 3, and then we want to move over how much? 0.01. So dy over dx is, what's the derivative? 4x cubed. So dy is 4x cubed dx. If we plug in 3, 3 to the third is 27 times 4, 108 times 1 over 100. You get 1.08. So if we move dx 1.08, we should move dy 1.08. So anybody want to estimate? Anybody have an idea of what 3 to the 3.01 to the fourth power would be? It's not 1.08. I move 1.08 from what? Yeah, what is 3 to the fourth? 81. So I move from 81, I move 1.08, and I get to 82.08. Whoops, sorry. .01 raised to the fourth power, 82.0854. So again, pretty close. And you can see where Newton was able to use a lot of different values to estimate. And last example, okay? The radius of a circle is measured and found to be 5.4 centimeters. So you got the circle and you're doing your very best to measure it. You're like, I think it's 5.4, but I'm measuring to the nearest tenth of a centimeter, and it's kind of hard to tell how accurate I really am. So if you measure the radius, the question is, if you know you're maybe within a tenth of a centimeter, how much will that throw the area off? Well, we have a formula for area. Area is equal to pi r squared. We know the current r condition. The radius is 5.4. And we also know dr. We know how much the change might be. How much? Yeah, 0.1. So now we just take the derivative. Derivative of area is area prime is equal to 2 pi r prime. Now, instead of attaching an r prime, you could just attach dr. It's the same thing as what we did earlier, right? So I've got area prime, is change in the area is equal to 2 pi times your radius, 5.4, times 0.1. I get 3.39. We're measuring area, so what should my label be? Centimeters squared. And, you know, the question is, how much is that? Is that a big deal or is it not? Well, the way we calculate what we call relative error and decide is a big deal or not is we take the error and divide it by the measured. In this case, it's measured area. So our error is 3.39. Our measured area would be pi r squared. So pi times 5.4 squared. We get 91.61. So I take 3.39 and divide it by that, and I get 0.037, or 3.7% error. So, you know, at that point, you can decide how big of a deal is it. If it's too big of a deal, then you got to come up with a way to measure it more accurately. Apparently, 1/10 of a centimeter is not enough. What is 1/10 of a centimeter? Millimeter, right? Millimeter, right? So apparently, to the nearest centimeter is not enough. Maybe let's go nearest millimeter. Better. Okay, so there you go. Assignment today is not all that involved. You should do fine with it. Just follow your notes.